In this example, we're going to look at electronic transitions within a hydrogen atom. So what's going on here is we have an electron that's going to be moving between different energy levels in the hydrogen atom. So there are two possibilities. It can either go from orbitals that are lower in energy to orbitals that are higher in energy, or it can go from orbitals that are high in energy to low in energy. When it does the first one, when it goes from a low energy orbital to a higher energy orbital, the electron is gaining energy. So that energy has to come from somewhere. And where that usually comes from is when the atom or the electron absorbs a photon. On the other hand, when it goes from a high energy level down to a lower energy level, the electron is losing energy. And that energy has to go somewhere, and it usually goes in the form of a photon that is emitted. So the equation that we have for what is the energy of these different orbitals is given by here, where the energy only depends on the principal quantum number, n. If I'm looking at changes in energy, then I'm going from one n value to another n value. So I would use this equation for calculating the change in energy when an electron moves from one energy level to another energy level. And the energy of the photon has to be equal to the change in energy. Now, the reason I have this in absolute values is because the energy of a photon is always going to be positive, but the change in energy for the atom or the electron is going to be negative when it emits a photon. So when it goes from a high energy level to a lower one, it's losing energy, so delta E is going to be negative. When it goes from low to high, the change in energy is going to be positive. So I need to keep that in mind. When a photon is emitted, delta E will be negative of the photon energy. When a photon is absorbed, delta E will be the positive of the photon energy. All right, so let's work this problem out. So we're told that the electron is starting in n is equal to 4, and it emits a 488 nanometer photon, and we want to know what is the value of n for where the electron ended up. And so what we're going to do is we're going to use the wavelength of the photon, and if I have the wavelength, I can get the frequency. If I have the frequency, I can get the energy, so that'll give us the energy of the photon. Now, because in this case, the photon is emitted, I know that delta E is going to be negative of the photon energy, so I'll be able to plug in my delta E here. I know the initial level is 4, and so the only thing I don't have in this equation is the final level, so I should be able to solve for that, and we'll do that on the next slide. Okay, so I've just kept here the most important information that we need. So the first thing I need to deal with is I need to get the energy of the photon. And so I'm going to use my wavelength and get that into energy. So the equation that I'm going to first use is that speed of light is the wavelength times the frequency, because then the second equation I'm going to use is that the energy of a photon is Planck's constant times the frequency. So I need to get the frequency first, then plug it in here. That'll give me the energy of the photon. Now, before I can plug in my wavelength into this equation, I need to get from nanometers into meters. So I have 488 nanometers. I know that 1 nanometer is 10 to the minus 9 meters. So my wavelength is 4.88 times 10 to the minus 7 meters. Now I'm going to rearrange this equation to solve for nu, so I'm going to divide both sides by lambda. So my frequency is equal to c over lambda. And my meters will cancel. I'll be left with seconds to the minus 1, and so my frequency is 6.14 times 10 to the 14th seconds to the minus 1. Okay, so now I can use this equation to find the energy, so I can just plug in my values. So E Planck's constant is joules times seconds. I'll multiply that times the frequency. So my seconds will cancel the seconds to the -1. And the energy of my photon is 4.0 times 10 to the minus 19 joules. Okay, so the energy of my photon is going to tell me what the change in energy of my electron is. Now, because this photon was being emitted, I need to make this negative when I plug it in for delta E up here. So let me scroll down a little bit. And we'll go ahead and plug those values into the equation. So I've got the negative of the photon energy. Is equal to and then times 1 over nf squared minus 1 over ni squared, which is 4 squared. Okay, so the first thing I'm going to do is divide both sides. So remember what I'm trying to do is I'm trying to solve for nf. And so I need to isolate it. So I'm going to get rid of this by dividing both sides by negative 2.18 times 10 to the minus 18. When I do that, I get 0.1867. And then I have 1 over nf squared minus 1 over 4 squared is 16. So I'll go ahead and put that in. So the next thing I need to do is I'm going to add 1/16 to both sides. And when I do that, I get 0.249 is 1 over nf squared. All right, so now what I'm going to do, I've got nf squared in the denominator, I want it in the numerator, I just have a 1 on top, so I'm just going to take the inverse of both sides. So 1 over nf squared is just nf squared, and I'll have 1 over 0.249. When I do that math out, I get 4.01 is nf squared. So I take the square root of both sides, and nf is going to be 2. It's not quite exactly 2, but it has to come out to be an integer. And so my final answer is that the final level that the electron relaxes to is n is equal to 2.